Oh, hi, Alan. Come on in.
Hi, Mr. Wizard.
Hi. See that thing up there on the bulletin board behind you?
Yeah?
You recognize it?
It looks like a maze, isn't
Yes, it's a very famous maze at Hampton Court in England. And you've worked mazes, I assume?
it? Yeah, you can get little games and things.
And
All
it's
kinds of
usually
things.
it's a mouse at one side
Yeah.
getting to the cheese in the other or something like this. Well, before you leave today, I'm going to show you the secret of how to work any maze the first time.
Any maze?
Any maze, yeah. It has to do with topology. Have you ever heard of topology?
I've heard of topography.
Well, this is topology. And in
Topology.
fact, you see these things here? A
Yes.
sieve, a spring, a watering can, and a stand, and well, all these things are related in some way, according to topologists. The men who study.
Related?
Yes. And I think before you leave, you'll be able to pick out and put into various groups these miscellaneous items.
I don't know. They don't seem to have any similar characteristics.
Well, let's start from the beginning. What do you think that word topology means? You said you knew what?
Topography.
What does that mean?
Well, that means the study of the surface of the Earth and the regions that different areas lie in.
Okay, now what then would you imagine topology to be?
Well, it's
The top part means
study. Well, top. I guess surface.
surface, right? And ology?
I guess studying of
The
surface.
study of surfaces. And by surfaces, they mean very complex ones, and that's a branch of higher mathematics that is relatively recent, you know, within the last 20 or 30 years or something. Or actually, parts of it had come before that, but really seriously studied. And today, you and I are going to have fun with some of the ideas and some of the tricks in it, and we're not going to get nearly as complicated as the real people who investigate topology.
Okay.
But let's start from the very beginning now. While it is true that it's a study of surfaces, we're going to start with just lines. And they study lines, but we're going to start with one of their simple concepts, a closed loop. And I'm going to, I have a puzzle for you.
All right.
Here's a rope, see it?
Yep.
And knots are part of topology because the idea that this is a line and it doesn't make them any difference what you do with it, it's still a line as far as topology is concerned, even though it's curved and crooked and all the rest of it. Well, my problem for you is I want you to put this rope in a hand like that, and I want you to now tie a knot in the rope.
That's easy. All right, I'll do it.
Don't let go.
I didn't let go.
Yes, you did.
When?
Watch. Try it again.
All right, here. I have the rope, right?
Yeah. Now, that means you're going to let go right there.
Oh.
You can't let go of the rope.
All right, so... Wait a minute.
See, it comes out again. Now, the reason why that's impossible to do, you realize, I think, without knowing too much about topology, is the people who study it say that a closed loop like this
Yes.
is a closed loop regardless of what you do with it. Even if you tie what looks like a knot like this, you know, that kind of a knot in it, that still is a simple closed loop.
Oh.
See?
It's the loop just
Yes.
tied up.
And you can't get a knot in it unless the knot is in the loop before it becomes a loop. See?
But
Now,
isn't that cheating?
well, now you can tie a knot in it, and you can't get that knot out
No.
because it's inside the closed loop. So what you have to do is somehow have the knot in the loop before you pick it up. You got it?
Got what? My arms?
Yes. Tie a knot in your arms.
All right.
Pick up that end here, pick up that end here, and now untie your arms.
Hey, I did it!
See? So when topologists study the closed loop, which is one of their beginning ideas, they say that it doesn't make any difference where the knot is, whether it's in your hands or in the loop, because really, when you put that and that together, that's all one loop, isn't it?
Yes, and you can't tie it.
No. So you put the knot in beforehand. Well, now the idea of the closed loop is an important one in topology, and here is another closed loop made out of solder. See it?
Loop?
A loop. Now I'm going to take the loop and distort it. It's still going to be a closed loop, though, right?
Messed up clothes.
A messed up closed loop. And I'm going to form it into notice I'm not changing the loop as far as its loopness is concerned. Now, I want you to put your finger in one of those loops and tell me whether it's inside the loop or outside the loop.
In any of these?
Yes.
Well, both are inside. I'll take this
no.
one, for instance.
Okay, now that one?
Yeah, that's inside. See, inside all of
No, remember that one. That's outside.
that? Yeah, how can it be outside if it's inside?
Well, now one way, of course, would be to pull it to see whether your finger was left on the inside of the loop. But topologists have studied this, and they figured there's a very simple way to do it without doing that. Watch. Here's another loop like that one, you see?
Mm-hmm.
Put your finger here on the outside.
All right.
Okay, now to cross into the inside, you're going to have to go over that line, right?
Right.
So put it in.
Jump over the wall.
Okay, now that's one.
One.
One line you've gone over. Now get it out. It doesn't make any difference where you go, whether you go out this way, that way, this way, this way. In order to get outside the loop, you have to cross over it once again.
Yes.
Okay. And to go back in, you
Jump
cross
in
it
again.
So now, start on the outside. If
Yeah.
you go over one line, you're in.
Right.
If you go over another line, you're out.
Right.
If you go over another line, you're in.
Right.
Another line, you're out.
Right.
Okay, now you can figure whether you're in or out on this one without ever taking it apart by simply, we took this one?
No, this
This one. Okay, now put your finger there and start out here. You know that's outside.
Yeah, that's
Okay,
outside.
we'll put one finger there and the other finger here. Keep that one in mind like
All
that.
right, so I'll use this hand.
Outside here.
Out. Jump over in.
In,
Out.
out, in,
I'm
out.
out.
Yeah, so you're on the outside.
That can be pretty confusing,
Yeah,
though.
well,
If you're
but-
outside, but you're inside.
Well, you're really outside that loop. In fact, try this one.
See, out,
Put your finger in there.
Out.
We'll keep track of it now. Okay.
out, in, out, in.
Okay, now hold your finger there. If it's in, when I pull it, it doesn't make any difference what I do to it. When I finish,
I should still
your
be
finger
inside
should be
the
on the
loop.
inside the loop. You see, it is.
It is.
Yeah, it is. Now, that idea of being inside or outside the loop is the basis of many plain parlor tricks. Maybe you've seen this one. Scissors,
Yep.
string, and a spool.
Mm-hmm.
And the problem is to get the spool and the string out from the scissors.
You
Separate
can't.
them. What do you mean you can't? Spool's too
It
big to
won't
go through the
it won't
handle.
go through the handle.
Now, if you want to do this at home, get a pair of scissors and you can put a button on it or anything just so it's big enough so it won't go through one of those.
You can
And
cut the string.
cut the string, that's not fair.
Well,
Notice, however, that that loop is a closed loop and that the scissors is not inside the loop.
it's not?
See, it goes in around here and comes around and doubles over here and goes back here.
Oh, it's just wrapped around.
So it's not inside the loop, so you should be able to get the loop out.
Well, maybe you think so, but, I don't know.
Well, see that end right there?
Yeah.
Pull that end up and loosen it up and follow around underneath through here and see what happens. That's it. Now bring it down underneath. Now do you see what you have to do?
Well, oh.
Go
put
the other way, over the top. No, the string over the top of the spool. That's it.
this.
Like that. And now pull the spool.
Right out. I didn't even use a knife to cut the string.
Yes. And now the point is that this loop is not inside that, and so therefore it's quite easy to do. And when you want to put it back together again, you go through like this,
Yeah.
see, and then work your way right back, and stick it over the spool. Like that, and then pull, and you got it right back on again.
There it is.
And there are many variations of this trick. Some work with a buttonhole, some work with two rings on the end of a string through various kinds of holes. And in fact, you know those wire puzzles that you have to twist to try to get loose? They
yeah.
look
yeah.
like they're linked, but they're not really.
Yeah,
Well, they're
they're-
based on exactly the same idea of a closed loop.
Well, now I know how to do all those puzzles.
Well, some of them are more difficult than this one. That's a relatively easy one. But anyway, in topology now, you see the idea of a closed loop, regardless of how you distort it, is still a closed loop.
Right.
Well, now let's go to surfaces.
Okay.
Here's a surface over here.
Piece of paper.
Piece of paper. And topologists describe this in a different way than you might. They describe it by the number of surfaces and the number of edges.
Mm-hmm.
How many edges does this have and how many surfaces?
Well, let's see. It has two surfaces, the top and bottom, right?
Top and bottom, and how many edges?
4. 1, 2, 3, 4.
In other words, there's one edge on each end and
Right.
one along each side.
Right.
Okay? Then, watch what happens. I have a piece of double-faced tape on here, you see. So I can put these two ends together, like that.
Right.
Okay, now that changes that figure very, very substantially. How many surfaces and how many edges now?
Well, you have two surfaces.
Two surfaces.
And two
Two edges.
Two edges.
Yes, two edges.
then this.
I got rid of two edges right here. I got by joining it. You see. So there's two surfaces and two edges.
Two edges.
Okay. Now, topologist then cut it in half. And what'll happen when you cut it in half?
You trust me with the scissors?
Yes.
Well, I
What
should
did you
have two of the loops.
All right. Try it.
That's simple enough even for me. Watch your finger.
All right.
There.
Okay, you got two loops, both with two edges and two surfaces.
I was right.
Okay. Now, that's the beginning. Now, let's start with a very famous strip called the Mobius strip.
Mobius?
Mobius.
Mobius.
Yes. Here's the double-faced tape.
Yeah.
And this time, I'm going to join the edges just as I did before. But all I'm going to do is one simple thing. Instead of joining them like this, I'm going to give that one a half twist.
What'd you do that for?
Well, now, that's going to substantially change the whole thing. How many edges?
Two edges.
How many surfaces?
Two.
Let's check. You hold that pencil down there,
okay,
right here at the joint, and make a mark, and I'll pull the paper, and we'll trace first one edge and then the other. All right? Go ahead.
There we go.
Don't lift the pencil up.
I'm not.
All right.
It's still there.
See what happened there? The joint.
Yeah. Well, where's the...
Yeah, well, keep going. All right. There. Still the same surface,
Still
right?
the same surface, yeah.
Can you see where you are?
Right back where I started. But I did it on both sides, and I didn't lift the pencil.
No, you didn't do it on both sides. There's only one side.
One?
Yeah. That's a surface that has two edges and only one, two edges and one surface.
By just putting a half twist in it?
By putting a half twist in it. This is a very famous strip in topology called the Mobius strip. So you can try that on your friend sometime. What'll happen when you cut it?
Well, if there's just one surface.
If you cut one surface in half, what should you get?
Two loops.
All right, try it.
Okay.
I'll feed it like an assembly line.
Yeah. Next.
There, now you cut it in half?
I have two loops. What? One.
Yeah.
Just one big one.
Yeah. So you see, topologists, as they begin to investigate these surfaces and edges and so forth, find that when you cut them, very strange things happen.
Yeah.
In fact, we won't try it now, but when you try this at home, just make that half twist in it and then cut it in thirds. In other words, cut 3 strips in it and see what happens. I won't tell you.
Okay.
What'll happen now if we give it a full twist?
I'm afraid to say.
That one was a half twist, right?
Yeah.
Now let's get it all straight. Here it is, ordinary.
Right.
There's a half twist.
twist.
There's a full
Full
twist.
twist.
Okay. How many surfaces? How many edges?
Let's see. You have two of the
2 edges.
edges.
Yeah. How many
I'm
surfaces?
not gonna say how many surfaces.
All right, let's see if we can
You
find out how
probably
many.
have about 3 now.
All
I don't
right, all right. Let's see. Start there.
know. Okay.
You got it?
Right.
All right.
Almost.
See where you are?
Right back where I started. 2 surfaces this time.
Yes.
Just like the before we put any twists at all.
Any twist in it at all. So therefore, by giving it a full twist, you got back to 2 surfaces again.
But what happens when you cut it?
All right, let's see if we can find out.
Different story.
Let's see what happens when you cut it. Do you think that it should end up with 2 halves like we had when we had 2 surfaces?
I don't think I'd better think. I
All
think
right,
I just
you
better
try.
cut. two loop.
Two loops, but one inside the other this time. You see what?
Quick way to make change.
What happened when you gave it the double twist? You in effect knotted them together,
Oh.
but they weren't cut apart yet. So when you cut them apart, they end up knotted together. That's amazing what'll happen.
Yeah.
What about a twist and a half?
Twist and a half, and that thing's gonna be in a lot of trouble.
Well, from what you found out, what happened when we gave only a half twist?
A half twist.
How many surfaces
It
do
only
we
had
have?
one surface.
So what do you suspect might happen here?
One surface.
Well, whoops. There's
There's
no
the,
twist.
No twist. Half
One
twist.
half twist. Yep.
Yep.
One twist.
And one and a
Twist
half.
and a half. Okay, now what do you think? How many surfaces? How many edges?
Two edges.
How many surfaces?
I'll take a guess.
Yeah?
Based on the other one, I'll say one.
Okay. Aha.
Uh-huh.
You want to jump over the bump?
Right.
There, thank you.
I lifted the pencil.
I know, but you put it right back down again.
All right.
Same surface. Yeah.
Whoa, what's going on?
Yeah.
Oh, there we are.
How many surfaces?
One.
One surface. By giving it the half twist. And what should happen now when we cut it?
Well, you'll probably have something like one loop with two little ones knotted together inside. I don't know.
You're not going to try to puzzle it out. You're going to try it. All
we'll
right,
just
try
cut.
it.
Now, what do we have?
How many loops?
Two.
No, one.
Oh,
But it's knotted.
yeah. Well, how'd that happen?
Well, you did it when we gave it a twist and a half. It formed
Oh, boy.
one long loop, just like the half twist did. But by putting a full loop in it, you got a knot.
That paper's pretty confused. That's all I can say.
Well, you can see there are all kinds of, in fact, one of the pages of the book that I looked at some of this material on had a whole series of figures. Two edges, one side, two edges, two surfaces, three edges, three surfaces. You can have all the different combinations. And by cutting them, you get all kinds of fantastic things. So maybe you ought to go to the library and get a book on topology and take a look at it. Because there are a lot of tricks that you can play by defining the number of edges and by twisting and so forth. Well, now then so far we've seen something with lines, the idea of a closed loop.
Mm-hmm.
And we've seen something about surfaces with a number of edges and the number of surfaces, plane figures like this. Now how about solids?
Solids?
Yes. These were all sort of plane figures, you see, or lines or plane figures.
You're not going to cut a solid, no.
No, but topologists do study three-dimensional objects and look at their surfaces and have defined them in a certain way. And those are those items I was playing with when you came in.
Oh, yeah. They all have something related.
Now, come on around on this side first, because here are samples of the various kinds of figures that we're going to investigate. Here is some children's clay-like stuff, you know, that you can...
Yeah.
And if you knead it into a sphere, it has one continuous surface, right?
Yes.
Okay. Now, notice that it doesn't make any difference if you put a thing in here like that. As long as the hole doesn't go through, that's still one continuous surface. And you can roll it out into this form, and that's still one continuous surface.
Right.
You bend it like that, that's still one continuous surface. In the same way that the closed loop remained a closed loop despite that you tied a knot in it, in the same way that the paper had certain characteristics, this has a characteristics and has a certain characteristic, and they have defined it as various genuses, various categories.
Genuses?
Genuses. And they have said, let us call this genus 0, because there are no holes in it. Now,
All
that's,
right.
that's not quite the way they define it, but for our purposes, that'll work.
Okay.
Genus 0.
Right.
Doesn't make any difference what its shape is, as long as it doesn't have a hole that goes all the way through, it's genus 0. And you see that these items over here? Can you find a genus 0?
This.
Yeah, a little saucer.
Right.
Okay. Now, let's put a hole into this material, and that's defined as genus 1.
Genus 1.
Has a hole in it,
Just goes in one little hole.
like a donut. Can you see an object over there that has a hole? One hole in it?
Yeah,
Well, now you mean to tell me this donut and that cup are related because they both have one hole?
It seems kind of odd, but
Well,
yes.
Can you form this donut into that cup without putting any more holes in it?
Yeah, but it'll be a pretty sick-looking cup.
Now, here, I'll put my finger in the
Alright.
hole, and that's the only hole you get. Can you form that into a cup?
Well, no. That's the handle right there.
Okay.
There's your cup.
But the hole didn't go all the way through, and there's
No?
a cup. And you see how that's that same figure, isn't it?
Well, not quite. It's
Well,
close.
topologically it is.
Yeah.
It has the same relationship.
So they are related.
Yes. Now what if I put a hole through there where you just made an indentation? I now have 2 holes. And obviously that would be genus 2.
Uh-huh. 2 holes.
Yeah, 2 holes. Can you make this into a sugar bowl has 2 holes, isn't it?
Yeah.
In the same way that the cup had only 1. These has
Right.
2 handles. Can you form this into a sugar bowl?
Well, I can try.
All right, I'll hold on to the 2.
All right.
Yep.
You got that?
Yeah. I'll turn them the way they belong. Okay.
Now just. There's your sugar bowl.
Well, it would have. Well, I see you put it. I see. Well, there it is. See
Yeah,
it?
great.
There's a little place for sugar there and a handle on each side. You'd be a great sculptor. I can
Wouldn't
see
that be great?
Point is that these 2 are very definitely related.
Yeah.
Now that hole that you made in there for this, if I make that go all the way through, we have 3 holes.
Genus 3?
Genus 3. And obviously there's only one thing left over
Pretzel.
here. A pretzel has 3 holes in it.
It's hard to believe that they're related, though.
And you can now see how you could form this into a pretzel, but if that's the best you can do with a cup and a sugar bowl, I don't think you'll want to try the pretzel. That's a little tough.
Okay.
Now, however, you can see that they could have 4, genus 5, genus 6, genus 7, depending on how many
Yeah,
holes,
anything.
for our purposes, how many holes they have in them. All right, now remember those items that you saw when you came in?
Yeah.
Look at them and tell me what genus they belong to. If it's 0 genus, it has no holes.
Uh-huh.
1 hole is genus 1,
genus
genus 2, and so forth.
Right.
All right? How about that
Starting
one?
with this?
Yeah.
Well,
A pipe.
A pipe. All right, it has 1 going in here. Well, that would be genus 1.
Has 1 hole.
One hole.
Continuous hole, even though it bends and whatnot.
Mm-hmm.
Okay, now, very good.
No holes.
No holes.
So that'd be genus 0, I guess.
Genus 0. Very good.
Now.
Watch for this one. Careful
Yeah.
now. Careful.
Well, it has 1 here, so.
Okay, so it's at least
it's
at least 1.
genus 1, right. Now, it goes around here.
Well, here, let me take it apart for you,
Hmm.
and you can see what happens
Yeah,
inside.
it goes around. Now, well, because of this, that would be another,
That's another hole, isn't it?
so that would be genus 2.
That's right. You see, when you put it together here, there's 1 hole here, and there's another hole in here.
Right.
So it's the same as a sugar bowl.
Mm-hmm.
Doesn't that seem amazing?
It's.
How about that one?
This, let's see. 1, right?
Where?
Here, 1 here.
Oh, the round one on top. Okay, 1.
2,
The square one sort of here, yeah.
right? And 3.
Yes, 3.
This doesn't look like a pretzel.
It sure doesn't.
It sure doesn't.
But topologically, it is very, very definitely related to a pretzel. All
Hard to
right.
believe.
How about
Oh.
that one? That's a glass tea that you use in chemistry, you know, for tubing.
Yeah.
What is it?
Well, it's at least 1 because of this.
Yeah.
And this.
Some people look at that and say immediately it's a 3 because it has 3 holes.
But they have to go all the way through. You see, there are 2 sides. So that this just, in a way, makes up 1, actually. It's just stretched out. So
Oh.
I'd say it was.
In other words, you'd say that this, if you forgot this side here,
Yeah.
this is like a great big long donut,
Right.
genus 1.
Uh-huh.
Now, if you punch another hole in the side and put in this, you have the next genus, which is what?
Genus 2.
Genus 2. So it's a genus 2. In spite of the fact that it looks like it has 3 holes in it.
It doesn't look like it's related to the sugar bowl.
How about the little watering can?
This, well, it's at least 1 because there's a hole here.
Mm-hmm. There's a hole here, though.
Right. But that doesn't go all the way through.
It's the same hole.
Oh.
Isn't it? The
Yeah,
hole comes in here,
that's
goes
right,
down,
yeah.
and comes out here. So it's at least 1.
At least 1. And this, oh, no, wait a minute. No, this isn't completed.
If that were completed here, it would be another hole, wouldn't it?
Uh-huh.
But it isn't. Okay.
Well,
How about the next one? So that's a genus 1.
right. This is genus.
Have any holes in it?
Well, not really. It's just wound up.
Yeah. So it's what?
I guess 0.
Okay. And how
It
about
doesn't
that?
look related to this, though.
How about that one?
Oh, this is about genus 1, 2, 3,
Yeah,
4,
you'd have to count them all. Anyway, you see how, in spite of the fact that these things don't seem to have any similarity to each other at all, you can classify them in the way topologists do by the number of, really they do it by the number of surfaces.
It's amazing.
Yeah. And in spite of the fact that we just played tricks with some of the ideas in topology, you can imagine if you were examining a surface that had many different planes to it, and if you wanted to get some geometric information out about it, the fact that you might study the topology of it, you could you know, make some quick shortcuts in finding out. So this is what topologists do. But now how about that maze up there? You remember?
Oh, yeah. Yeah.
I said I was going to show you how to solve it.
Uh-huh.
Well, you remember that loop we made out of a wire solder?
Yeah.
Consider this is ordinarily a hedge in the one at Hampton Court in England. Consider that a loop. The black edge here is one side of the loop, and that black edge is the other.
Side.
Well, remember how if I took this and formed it into this maze, all you'd have to do is follow one side.
Right.
So go into Hampton Court maze or any other maze, put your left hand on the wall, and never take your hand off of that wall and trace it.
All
and
right.
watch, you'll think you'll be able to get inside. Right in there. Notice how you don't back up? You constantly move because you're keeping your left hand on that wall?
Yeah.
All right.
What happens when I get there?
Well, you watch.
Hope there's a place to sit down or something.
That's right. Now, there you go. You got into the center. Notice you didn't make any errors.
No, no.
And in the center here, there's a place where you can sit down and rest. And however, this works now with any maze, not just with the Hampton Court maze.
Any maze?
Any maze. Anytime you get one of those rabbit getting into the pen or the cheese and the mouse or the knight and the lady or something, just pretend that the line itself is on one side and you follow it around because it's really a closed loop. You'll also find, if you came in here,
Yeah.
okay, all you'll have to do if this is really as a closed loop is stay right on this, work your way around like
right
this,
out.
and you'll get right back out again because this is a topologically closed loop. Try it.
Next, just when you thought you knew it all, find out more on The Secret Life of Machines. It's TV Science Classics Weekend, next on the Science Channel.